Okay, this is lesson 6D, second part. So we're going to do a full confidence test here, or significance test, I should say. That was the homework. Okay, so we're going to put it all together. We're going to do our first full one sample z-test for proportions, or one prop z-test is another way of saying that. I usually use the calculator notification there, so one prop or one proportion z-test. So we're going to talk more about how to use the calculator to do a test here, but you can do that instead of the do step. But you must state two things, the z value and the p value. You don't have to say the calculator command you use to get it. You just have to say those two values. Okay, a potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8% of the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. They have standards. The potato chip producer has just received a truckload of potatoes. A supervisor selects a random sample of 500 potatoes from the truck. That seems fair. An inspection reveals that 47 of the potatoes have blemishes. Is there convincing evidence at the 10% level that more than 8% of the potatoes in the shipment have blemishes? Okay. So what is it we want to test? So let's kind of do that or talk about that first. So what is the null and the alternate here? So clearly we are talking about proportions. There's 8% there, that's a proportion. So P, you want to say it in words, is the true, I like to say the word true when I'm describing a parameter there, true proportion of what? So in context, true proportion of the percentage of trucks or proportion of trucks that have more than 8% blemished potatoes in the truck, something like that. So the null is that P is 8%. So 0.08. The null, the alternate, is that we do have a direction here. We think it's greater than 8%. So we think we should send the truck back. That's what we're trying to disprove that, hey, we think more than 8%, maybe. Let's see what they said here. So, oops. Yeah, same null. Also a good idea to mention the alpha level. So in the alpha level is unusual here, so it's really important to mention that. So I should have written down alpha equals 0.10. So this is not a life or death situation. They just decided to change the alpha level to 10%. So let's see if that makes a difference here. So do one sample z-test for our proportion. So you want to check the conditions here. So what are the conditions for this one? So does it say something about a random sample? I see, random sample of 500 potatoes. So random, this is checking the conditions, sample. It'd be nice if you said 500 potatoes. That's check. By the way, somewhere on here, it's a good idea to write one proportion z test. That's what we're doing here. And so somewhere on your paper, write that. It's at the top of the paper. If you were in class today, I probably gave you a sheet of paper that looks like, let's see, probably like this, right? And so it's at the top of my paper, but again, you could call it one sample z-test for proportion or just a one prop z-test, but that gave you like just the nuts and bolts of what we're doing for an order here. So the second condition, or one of the conditions there, is large counts. So let's do n times p, so 500 times 0.08, and then 500 times 0.92. That's going to be p and not p hat there. So let's see. Let's just do that. I'm not thinking yet this morning. Okay, so 500 times 0.08 and then 500. So that'd be 40 and then 460. 40, maybe 460. So both of those are greater than or equal to 10. So it does pass the large counts, which means we can do a normal curve. Less than 10% condition, so 500 is certainly less than 10% of all the potatoes on that large truck, of all the potatoes on the large truck. Okay, so we checked the conditions. And again, they did use the, that was silly. So it should be 0.08. I don't know why they have 80%. It should be 0.08 and then 1 minus 0.08. I think that was just a mistake there, but they had the right numbers, interestingly, the results. Yeah, the big key there is we don't use the p hat there. For test, we use p. For proportions, we use p hat. Is there convincing evidence? So we might have some evidence. What is the evidence we have? I'm curious. So 47 divided by 500. Okay, so 9.4%. So we have some evidence, but is there convincing evidence? So you really probably want to do the do part here. So if the conditions are met, we're going to do, not a bad idea to write p hat here, which was 47 out of 500. That usually helps you kind of type it in the calculator as well when you get to that step, if you get to that step. So Z is the, so it's p hat, which again was 0.094, minus P, which is 0.08, over the square root of, I think this is using the P value there, 0.08 times 1 minus that, which is 0.92 over 500. You want to type that in your calculator to get an answer. I guess when you type it, let's see, so square root of 0.094 minus 0.08 over square root of 0.08 times 0.92 over 500. So 1.154, 1.1, a little more than 1 standard deviation above the mean is where this ends up being. So then you could do your norm CDF here. The norm, well, let me just get it from the menu here, menu 652. So our lower bound is 1.154. And then we're going upper bound of infinity, or a very big number, and leave the default 0 and 1. These are z-scores, so that should give us the value. So our p-value equals 0.124. So 12.4%. Okay, so we did the do step there. If you want to do that all in your calculator, you are allowed to do that. So menu, where would that be? Probably stats. And if you see that last choice, stat test, and this was a 1 prop z test. So the null is 0.08. The number of successes, remember 47 out of 500, so 47 out of 500. And then the alternate was greater than, I believe, greater than that first choice. And it gives us 1.154. Gives us C is 1.1. Yeah, that p-value is 0.124. Everything's the same there. So it really does work. If you do that, make sure to say the p-value and the z-value. They want to see both of those numbers for sure. I like p-hat on there as well, but those two are the two you have to have on there. They drew it, which is really a nice move there. I like that move. It helps you, what is the definition of p-value? Assuming the null is true, that's the middle, is 0 in this case, because z-value is 0 there. What's the chance of getting a result of a z-value of 1.15 or more extreme than that? So we're shading to the right there. And so that really just helps you figure out which way the norm CDF goes when you do that in your calculator. Okay, so then again, I like to go to the script here. So the script is at the bottom there. Because our p-value of 12.4% is greater than the alpha level of 10%, we do not reject it all. We fail to reject it all. There is not convincing evidence that the true proportion of blemished potatoes is greater than 8%. So something to that effect is what you want to say. Let's see what they said. Because the p-value of 12.4% is greater than the alpha level of 10%. Great to say both of those exact values. Don't just say because p-value is bigger than the alpha level. We want you to know, hey, what are those numbers? We fail to reject. We do not reject the null. We do not. There is not convincing evidence that the proportion of all potatoes in the shipment with blemishes is greater than 8%. Great. That is full-on significance test, one proportion z-test. So yeah, I mean, that's what I like to say, or at least think it. We do not reject. We do not have evidence. That's the most common error I see. They oftentimes students will do, we do not reject. We fail to reject, and then they say we have evidence. No, if you didn't reject, you don't have evidence. Okay, so now just one more concept of the day. So we finished our full one prop z-test. This is type 1 and type 2 errors. This is important to understand. So it occurs if we reject the null when the null is true. That is, if the data give convincing evidence that the alternate is true when it really isn't. Okay, so type 1 error occurs when we reject the null. We think there's something going on, but actually the null was true. So you made a mistake, right? The data, you know, we thought we were trying to do the right thing, but we made a mistake. That happens sometimes. That happens. Okay, so then type 2 is when we fail to reject the null. We don't reject it, but actually the alternate is true. The null is not true. I like this little chart. This helps me. These are the correct conclusions. If you find evidence to reject the null, you've rejected it and correctly concluded that the alternate is true. If you didn't find enough evidence, then you didn't reject the null, and we think the null is true. That is, those are correct decisions. This is a type 1 error, is when you reject the null, but actually the null is true. Type 2 is when you fail to reject, but actually the null was false and the alternate was true. Let me stop this for a second. So I really want you to add these words to that chart. So top left, not only is that a type 1 error, that's what's called a false positive, right? We think, you know, we get a positive test result, but actually, like as if you So when you get a false positive, you rejected the null, but the null was true, right? And that's going to be our alpha level there. So that's when you actually rejected, but the null was true. You shouldn't have rejected. That's called a false positive. And the other mistake, the type 2, is a false negative. That's when you did not reject. You didn't have enough. You felt like you didn't have enough evidence, but actually the null was false, and you should have rejected, but you didn't. That's called beta. So those are helpful to know the alphas and betas there. I want you to add that to your chart because it's just helpful to think about. This is a weird concept. You have to kind of wrap your head around, but I like it. It's something you need to know. Okay, same potato chip thing. We already did that. Describe a type 1 error in this setting. So let's go back to that idea here. So if you look at the chart here, so type 1 error is when you reject, but the null was actually true, right? So that means, we reject. In this setting, what would that mean to reject? We send the truck back. but actually they didn't have more than 8% blemishes on the potatoes. It was a perfectly good truck. Like it was good enough for us to take, and we sent it back. And boy, that's going to make the truck, the supplier's guy is going to be mad. He's like, this is a good shipment. You sent it back. Like, what's going on here? They're going to be mad at you. I don't know if they'll keep doing business with you. It could be a problem. You could have used those, and you sent them away. It's bad for the supplier, but it's bad for business, right? It's just not a good way to conduct business. So a consequence would be the potato chip producer sends away the truckload, wasting time, depriving the supplier of the money, right? So it definitely hurts the supplier and your just business in general. What's a type 2 error? So let's think back to what a type 2 error is. So that's when you fail to reject, you should have, and the null is actually false. So this is bad too. So we should have sent this shipment back, but we didn't. We kept it and used it, and there were tons of blemishes on those guys, right? So now our customers can be mad at us. They're like, how come there's so many blemishes on these potato chips? Because when you cut them up, that's what happens. So possible cut are made with blemished potatoes, which may upset customers and lead to decreased sales. Either one is bad for business. You want to make the correct decision, right? That's what businesses want to do here. Okay, now they add this extra here. So type 1 is equal to alpha, right? So that's true. Type 2 is equal to beta, by the way, which is helpful to know. We'll get there eventually, I believe. So a few more questions. Data from the Pew Research Center suggests that 36% of all U.S. teens say they spend too much time on social media. Administrator for a large university wonders if this is true. Students at the university, the administrative surveys a random sample of 400 students and finds that 167 say they spend too much time with social media. Is there convincing evidence at the 5% level that the percentage of students who spend too much time differs from the national percentage? So this is what you would do. You go through all the steps, right? State the null. I would recommend just kind of stopping this and doing this on your own. See if you can match it up. Null is P is 0.36. Alternate is not equal to. So the reason for that is the last sentence there. Percentage of students who spend too much time on social media differs from the national percentage. So they're not saying it's greater or less. They're just saying, is it different? So that last sentence, that's why it's not equal to. P is the true proportion of all students at the university who spend too much time on social media. There's a one sample z-test. Make sure to say that somewhere. Random sample, 400 students, less than 10%. 400 students is less than 10% of all the students at a large university. Large counts, again, use P for that. So 400 times 36.36. Those both have to be at least 10. Then do your p-hat, or you could do this in the calculator, right? So you could get your calculator out and go, let's do this one in the calculator. So you'd go menu 675, I believe. So the null is 0.36. Number of successes, it was 167 out of 400, I believe. And not equal to is the default, which is what it was. And so we should get the same values they did. You want to make sure to say the z values, 2.396. And the p value is 0.0166 if you round it there. So 1.6% is less than alpha, right? So we do have evidence, we do reject the null, we do have convincing evidence that the percentage of students in the university who spend too much time on social media is different from the national percentage. Notice this is a two-sided test. So if you did norms CDF, you'd have to take the side, do 2.396 to infinity, and then double that. So you actually have to double the norm CDF if you do that. 2 times 0.0083. Police department wants to find out, determine if it's worth the cost to install a speed sensor and a traffic camera on a highway near the city. The department will install speed sensors and traffic cameras. I hate speed sensor, I'm not happy about that. Traffic cameras and more than 20% of the cars on the highway are speeding. Please select a random sample, and it's tested at the 5% level. So P is 0.2, and they think it's greater. They think more than 20% are speeding, so it's greater. Okay, so this question is, we don't do the test. We just have to describe what would a type 1 error be in this setting and give a possible consequence. So again, type 1 error is you reject, so you find convincing evidence. So we rejected, but actually the null was true. Oh, we made a mistake. Okay, so we rejected, so we think, the police think there's more than 20% that are speeding, but actually not more than 20% are speeding, right? The null is true, like it's fine. So they're going to install all this stuff, waste all this money, and actually not that many people are speeding. They could have probably used a different, could have set up, spend that money at a different intersection or a different area where it would be more profitable for them to give out lots and lots of tickets. Type 2 error would be what? So that's when you don't reject, but you should have rejected. Actually, the null is true. So here, now they would decide, oh, we're not going to put in the speed camera and all the cameras and stuff because these people aren't really speeding that much. And actually, like, there's a lot of speeders, and they should have done it. So this is what they said there. If you're having trouble remembering a type 1 error, a false positive, which is, by the way, the alpha level, this would be the slide for you. So that would be like a doctor telling this guy, "You're pregnant." I don't think he's really pregnant. That would be a type 1 error when you think. So it's called a false positive. Type 2 error is this nurse or doctor telling the patient who clearly looks pregnant, "You're not pregnant. You don't have to worry about anything. You're not pregnant there." So that would be a type 2 error. There would be consequences, I guess, for each. That would be interesting, but I thought that was funny.